why didn't, the science was becoming clear, why didn't you do something? Our understanding of global warming, climate change, is, it's often said it's based on climate models. That's not really true. The most important and detailed information that we have about how sensitive the system is and how it will respond as the boundary conditions change, including the atmospheric composition, comes from the history of the Earth. We have detailed records of how the Earth responded in the past to those changes. And also, second on the list is the observations of what is happening now. We now have satellites, we have ways of measuring accurately how many things are changing in response to these rapid changes in atmospheric composition. And climate models help also. Now, I'm not going to, I would love to talk about paleoclimate, but I'm going to do only a little bit of that because it's 45 minutes doesn't give me too much time to do too much paleoclimate, but I will do a little. Now, one thing in terms of what's happening now, we began to make satellite observations of the sea ice in the Arctic in the late 1970s, and what we see is that the amount of sea ice fluctuates from year to year depending on the weather that year in the Arctic. But there's a strong downward change in the amount of sea ice. It's decreased by more than 30% over the last few decades, and within 20 or 30 years, we will probably lose all of this ice in the warm season at the end of the summer. And that raises questions about the stability then of the Greenland ice sheet and the stability of the frozen methane that's on the continental shelves off the coast of Canada and Siberia. Another thing that we're observing is the melting. We can observe from satellite is the area that has summer melt on Greenland. And that too, as shown by the line graph, it fluctuates a lot from year to year depending upon the weather that summer. But you can see that there is a trend toward more and more larger and larger area with summer melt. And that meltwater does not make it to the edge of the ice sheet in general. It burrows a hole in the ice sheet and goes to the base of the ice sheet where it lubricates the ice sheet and causes these giant icebergs to be discharged to the ocean more rapidly. We didn't know for sure what the impact of this warmer climate was on the ice sheets because increased temperature also causes the atmosphere to hold more water vapor. So there's more snowfall in the winter, which makes the ice sheet thicker. But common sense tells you that as the planet gets warmer, the ice sheets are probably going to get smaller. And now, beginning in 2003, we began to measure with the gravity satellite, GRACE, which measures the gravitational field of the Earth with such a high precision that we can accurately track the mass of the Greenland ice sheet and the Antarctic ice sheet. And the ice sheet gets heavier in the winter as the snow piles up, and it loses mass in the summer. But you can see it's losing mass overall at a rapid rate. And what is particularly important is the recent update to these curves, adding the last 2 years of data, makes it clear that the rate of mass loss is actually increasing. Greenland was losing mass at a rate of about 150 cubic kilometers per year. Well, it's now about 250 cubic kilometers per year. And Antarctica was losing mass at a rate of about 75 cubic kilometers per year. Now it's about 150. So there's been almost a doubling in just several years. Another expected effect of global warming is an expansion of the subtropics as the rising motion that occurs in the equatorial region and the subsidence that occurs at somewhat higher latitudes, which causes the existence of the subtropics, that circulation cell is expected to expand as the planet gets warmer. And what we observe empirically is that it has expanded by about, on average, around all longitudes, on average it's expanded by about 4 degrees of latitude. And that's already beginning to affect regions like the southern United States, where Lake Mead and Lake Powell are now only half full, and the Mediterranean region, and I would say it's also affecting Australia, because it causes the jet streams to move slightly poleward, and of course that doesn't mean that and by the way, another impact of this increased dryness is an increase in the fires, which is noticeable. There are other factors that affect the fire frequency and intensity, but there is a tendency for fires to burn hotter as the planet is getting warmer and drier in these regions. And there are other factors that affect rainfall. So, for example, the ocean temperature patterns, the ocean temperature in the Indian Ocean and the El Nino, La Nina oscillation in the equatorial Pacific, and the temperature of the waters around Australia will all influence rainfall in Australia. And in general, because the ocean waters are getting warmer, you're going to get, when you do get rainfall, you can get heavier events, more extreme rainfall events. But overall, when you average over decades, you're going to see, I think, a more intense subtropical type climate in much of Australia, and that's an effect of global warming. Another thing that's happening is all around the planet, glaciers are melting. And by the way, here's a case where you probably heard, this is part of what I call the great hoax. In this telephone-thick IPCC report, there was a mistake with regard to Himalayan glaciers. It said Himalayan glaciers would be gone within 25 years. That's not true. The Himalayan glaciers are the highest and the thickest on the planet, and they're not going to melt that rapidly. But the main point is that glaciers are melting all around the planet, in the Rocky Mountains, the Andes, the Alps, the Himalayas. We have a national park in the United States called Glacier National Park. Within 25 years, it will have to be renamed Glacierless National Park, because the glaciers are melting, receding so rapidly there. And this has consequences, because there's a couple billion people who depend for fresh water on rivers which originate in the mountains, where melting glaciers in the dry months, the hot months of the season, have more than half of their water coming from melting ice. So once those glaciers are gone, you will have bigger floods in the spring as the snow melts, but you will have seasons in which the rivers are tending to run dry. Another effect of global warming and increasing carbon dioxide is on coral reefs, which are under stress for several reasons, but two of the more important ones are the increasing ocean temperature, which can cause the corals to bleach, and the acidification of the ocean. Those species that have carbonate shells or carbonate skeletons cannot survive as the ocean becomes too acid. It will dissolve the carbonates. So looking at all these different sorts of evidence for what would be the safe level of atmospheric carbon dioxide, we come to the conclusion that it's no more than 350 parts per million. And one of the most important ways of concluding that is just looking at the radiation balance of the planet. The increasing CO2 causes the planet to emit less radiation in the infrared part of the spectrum because it makes the atmosphere more opaque for the infrared radiation, so the emission comes from a higher altitude where it's colder. And that the amount of energy coming in from the sun is unchanged by the added CO2. And so you get a planetary energy imbalance with more energy coming in than going out. And where does that energy go? It goes mostly into the ocean because that's where the large thermal inertia is. And now, and this is so if we want to restore the planet's energy balance, well, we know from measuring the rate at which the ocean is accumulating heat that that imbalance is about 3/4 of a watt. If we wanted to restore the planet's energy balance and stabilize the climate, we would need to reduce the CO2 and other gases enough that it increased the emission to space by 3/4 of a watt. And that implies that CO2 would have to be less than 350 parts per million. So if we want to preserve the planet that has existed the last several thousand years during this relatively stable climate of the Holocene, we would need to reduce CO2 then to less than 350 parts per million. And I wanted to mention the fact that the science has actually become much clearer in the last half year or so. One of the things, when I wrote the book, I could only say that it seemed that the planet was out of balance by at least half a watt, or approximately half a watt, based on the measurements of the ocean. But in fact, what our model said was it should have been out of balance by about 3/4 of a watt. Recently, the results from the measurements of the Argo floats, they're beginning early this decade. The different nations of the world began to put out these floats, which, and there are now a couple thousand of them. Every so often, they release an instrument package on a wire, which yo-yos down into the ocean to a depth of 2 kilometers, and then it yo-yos back up. And it measures the temperature of the ocean and the salinity and some other quantities. But it allows us for the first time to see how the heat content of the ocean is changing. And it turns out that it's gaining energy at a rate of about 3/4 of a watt per meter squared. So it makes this, and this is really the smoking gun for proving that humans are the cause of the climate change. Because if this were a natural fluctuation, say the ocean just, its circulation changed so warmer water came to the surface, well then you would get more radiation to space, not less. So it shows that it is a forced climate change. And we know the natural forcings. We're measuring the sun's brightness very precisely, and we know the volcanic aerosols in the stratosphere. So in fact, it is, it's exactly what we calculate it should be. So it really is a confirmation of the basic phenomena. The ice sheet mass balance, I already mentioned that ice sheets are losing mass more and more rapidly. At the time I wrote the book, I didn't know that the curve was actually turning down. And at the time I wrote the book, I had to say that we were stuck. We had been stuck for a couple of years in the deepest solar minimum during the entire period of measurements from the 1970s to the present. And it wasn't certain that the sun would come back out. The sun has this 10 to 12 year cycle in its brightness. But there were times earlier, the Maunder minimum in the Middle Ages, not the Middle Ages, the 1600s, when the Little Ice Age time, when the sun did stay in a minimum for a few decades, and that was presumably at least a major cause of that cool temperatures. Well, but the size of that climate forcing we can compare very accurately to CO2, and even if it stayed in that minimum, it would be equivalent to about 7 years increase in CO2. So it wouldn't change the fact that the planet is going to keep getting warmer if we keep emitting CO2. But it would have caused, it would have reduced the rate. But now what we see is the sun is indeed coming out of its solar minimum. It's going to be a normal, apparently, solar cycle. Okay, so we could get back to 350 parts per million, but what we need to do is look at where this CO2